Um, you might want to know why I picked this topic. Seems the receiver LOS is pretty common in fiber optic communication. The reason is this. Recently, I saw some data sheet. They just removed the LOS. And I understand because people might not use it. And also what is important to mention is that the LOS is not in any MSA documents. So it just provide a user with some tools to help their system. And that's why it triggers me to do this topic in the webinar. And I just want to let you know that what are the important things you can do with this signal, as a designer. So I would concentrate in two areas. Why do we need receiver LOS, which is the loss of signal? Secondly, I want to provide some details to you in how people design this LOS and some applications. So hopefully that will be useful for you. And why do we need a receiver LOS? First is to flag the user when the input power falls below a certain level. And if the LOS is gated with the system link status, it can trigger the link loss alarm. Yeah. The receiver LOS is very often combined with the LOL, which is the loss of log inside the receiver CDR, to increase the reliability of the flag. And I will show you more on slide number 9. And also people are now using the LOS for bit error rates. And I will show you some on slide 10. And this bit error rate requirement happens in the last maybe 5 years. But I think it's very useful too also. And lastly, SD, which is signal detect, is just the opposite of LOS. So some people use SD, some people use LOS. Okay. So the first question I would ask you is that do you know the receiver LOS can be average receiver input power or can be modulated input power? So in the next two slides, I will show you the basic differences. On this one, on the first one, I would explain the average power detection, which is been with us for many, many years. So on the left side is a pretty typical laser Li curve. Nowadays, all lasers are biased like an AC couple. So when the input data is absent and the output power indicate here, it becomes average power to the receiver. So it will be the same with and without the modulated signal, right? So I just put a very simple diagram, and then this pin current detects the average power, and then it goes into some monitor to trigger the limiting amplifier for LOS signal. So keep in mind that there is a signal coming in, there is a threshold that you set the LOS level. So to conclude on this scheme, for average power detection, when the transmitter input data is on, the transmitter average power is detected by the receiver. When the transmitter input data is off, the transmitter average power is also detected. There's no difference, right? Because simply due to its AC coupling. Now, what I want to focus a little bit more is the next slide, which shows you the peak power detection. Again, I use the same laser Li curve. So when so let me go through this scenario. When the transmitter input power is on, the transmitter peak power is detected, right? So when there's a data here and the peak power, like I indicated by dotted line, is detected in after the AC coupling cap inside this receiver. But when the transmitter data is off, right? When it's off, now it will be on the transmitter. It will be here. It's like an average power. But however, something happened. There are two scenarios when the transmitter power is off. One is that the transmitter is not chattering, right? Chattering, that means there's no noise on the transmitter power when the squelch is on. And in that scenario, the transmitter peak power is not detected, right? Because there is nothing except a DC line. Scenario number two, when the transmitter squelch is off, transmitter peak power is detected simply because let's go to this picture here. This is like a very typical laser driver input circuit. You can see the bias voltage is here. They are both very closely together, the data and data bar. So under some condition, when there is no data coming in, but the transmitter is in a noise environment, for instance, there is some noise spike here, can trigger the modulation onto the laser. So we call it chattering, right? Chatter. So, or under temperature, the threshold bias, the bias voltage got moved, and it will be very vulnerable to noise and to trigger again. So under some conditions, and here is the average power from the scope. You can see the noise coming in here. We call it chattering. So to simply put, when the transmitter data is off, when there is no transmitter squelch. Now I will explain the squelch on the next slide a little bit more. The detector, the receiver will sense this noise and then think there is a peak power coming in. So it will affect the LOS function. Okay, so that's what I try to tell you. It happens this way. On the next one, and yeah, on this one, and then I just tell you that there are 3 ways you can do. First of all, you check your EEPROM table to make sure LOS, transmitter receiver, LOL, or squelch is implemented on those 2 bytes. You can read the MSA spec, but its detail is provided in this by these 2 bytes. And then also you can check the flag. This flag can be checked on byte 3 and byte 5 on the lower memory. And what the last one tells you is that you can control the receiver or transmitter squelch on page 3 by 240 if the squelch is implemented by those 2 bytes. Okay, so it's very useful. Squelch, that means you can squelch the transmitter output, right? When there is no data coming in, so there will be no noise, but the transmitter level will be set at the same level or at different level. It depends. And when there is no squelch, there's no different than from before. From the chattering of noise, it can happen. The next slide shows you the relationship in between the LOS assert and LOS deassert. Basically, those two parameters, the difference of those two parameters is what we call hysteresis, is LOS deassert minus LOS assert, which is 20 log of the voltage deassert over assert. Keep in mind that it's already, this is in the power term, right? 20 log is the power. So whatever this represents is the power, if you take 20 log of the difference. And what I'm trying to show you is that the hysteresis tend to be much smaller at the low input power and tend to be bigger at the output, right? Basically, it's because at the low input range, the noise is much bigger. So the noise itself, you can see the input line and the threshold line, they can both carry noise. So at a low input level, it will the LOS assert will be triggered faster, and then so as the deassert. So this is provided in the IC, the limiting amplifier IC datasheet. When you do a design, you can look it up. It should be there. And here's a little explanation of the LOS deassert and LOS assert. And on this curve right here, the y-axis is the alarm, can be on or off. And on the x-axis is the input power. Now let's go from the high power to the low power. As the attenuation starts to increase, so the power becomes less, and then go to a set points, which is set by the threshold, and then it kicks in, and then goes to alarm, right? Alarm, and then it will remain alarm for whatever input power is equal or less than the LOS assert points. Right? The way to get it back, to go through the hysteresis is when you start to increase power from very low to higher power, and it goes through this cycle, and then it will pass LOS assert, and then go to the what the hysteresis is defined, which is half dB as the minimum level. That's what everybody specifies, and then it would go to the deassert, and then which turns off the LOS alarm. Okay, I want you to pay attention to this number. Now, if this number cannot be too small, if it's below half a dB, you're in trouble of oscillation. You can see, right, if they're both side by side. And let's go back to this diagram. If they are both side by side, almost the same, the output would be on and off, on and off. So because whenever it triggers, the IC would generate some spikes, and it would loop back into the input line to re-trigger. So when the hysteresis is too small, you will have LOS oscillation. Okay, so usually I think a good number would be like a 2 dB. You know, 1 to 3 is okay, and don't get it too big. If it's, people set up pretty big, like a 5, and then that defeats the purpose of monitoring, right? So the other here is how you gang up the LOL with LOS. So to improve the reliability, there is one case I want to tell you here is a must to gain LOL with LOS. Number 2, in the absence of input signal transition, right? When there is no transition in the input power, the LOL, the loss of log, may fail to turn on even though the CDR's frequency is off, it's drifting off. It will not, it will stay on, it will not trigger. So in that case, if we gang up the LOL with LOS, the LOS would automatically because since it's all together, it will trigger alarm. So this is a very, how to say, safe way to do it. So to stabilize this number, you don't want a false triggering on this. The other one I want to talk about is a little bit, and basically the way to do it is very simple, to combine the LOS to indicate the bit error rates, right? Basically, all you need to do is to do a lookup table in the firmware to calibrate the bit error rate versus input power or input peak-to-peak power. It doesn't matter, and up to your preference. So you have a table inside your firmware. At each different input power, LOS will trigger, right? So that will indicate the bit error rate. I think the very common bit error rate is like a 1 to the -4. I see some system, they put up a system spec for the transceiver vendor to do so. So I think it's very useful, but you must calibrate your system to do it. And the last one is just I want to do a summary. And I talk about receiver LOS, and it can be single link status, gate with a CDR LOL, or it can be used to track bit error rates. The type of receiver LOS can be average input power or modulated input power. There are three schemes. One is average power detection. The other one is modulated detection with transmitter squelch on. And the third one with the modulated power detection with the transmitter squelch off. So there are three scenarios for LOS. And I talk about how to design the LOS briefly and the pros and cons. And I also talk about the hysteresis, the relationship in between the LOS assert and the assert, and some caution how to use it. So this is the end of my webinar, and I welcome question from you. If you have any question, you can type it in and I will answer you. Are there any questions? There's a question. What is a common application you have seen? It's a link detection, right? So the simplest term is that people use this LOS like a flag to indicate the link is on or off. Now, I think what can be a little bit better is to if the user specify LOS at a certain level, right? So LOS, if you specify LOS level below your sensitivity level, that means lower than your sensitive level, and you might not have, you probably would, the customer would see the error before the LOS flags it. If you specify too early, that means much higher than the sensitivity level, that you would have some false alarm at some range. So to specify where the level is, it takes a little thinking. So it should be outlined in your product spec for your customer. Yeah. Are there any other questions?
There's something in the chat box. Can you see that one? Yeah.
Okay, let's see. Okay, I see. Okay. Any of the threshold level and then all of his traces are adjusted via I2C register programming That's a very good question. Usually this number is fixed, right? It's like a define LS on and off, right? Now, it can be different function aside from the EEPROM table, right? EEPROM table tells you how to turn it on and off, right? But the level, if the level is variable, yes, it can be if the limiting amplifier, I2C, can allow you to change the set points. You can go into, usually your firmware link into your limiting amplifier firmware. So yes, it can be done, but it's not simply just like a change something quickly a bit in the EEPROM table. It needs some more engineering, work. Could you repeat the question? Okay, let me repeat that one more time. Any of the threshold level and or hysteresis adjustable via versus I2C register programming. And sorry, I don't know all the details of CMOS. CMOS is just like a 200 to 400 gigabits MSA spec management interface spec. The other spec I want to mention is FCC 8636, which is what probably you have for 100G and down. So basically so is in what I mentioned, those registers are in the 8636 spec. So there's another one. Thank you, Eric. Is the CMOS 4.0 and 5.0 coming soon? Yes. Well, I think it's coming. The 4.0 definitely is there. I don't expect too much difference. I think 4.0 is very advanced. So So I don't know about 5.0 at this moment. Okay, so that's about it, Priya.
Yes, thanks, Eric, for the presentation, and thanks you all for joining. We hope you found it useful. So if you have any questions about the presentation material, you can reach out directly to Eric or send an email to info@vitextech.com. Like I said, all our archived webinars are on our website. I dropped a link to it in the chat. This presentation also will be going up by tomorrow on our website. The next webinar is scheduled on 28th, and the topic is 100G ZR transceivers. You will receive an email from me with all the registration details. Thanks everyone for joining once again, and have a wonderful rest of the week. Bye.
Thank you, everyone. Bye.